Okay, let's go ahead and get started. We have a quiz on Friday. Other than that, we a help session, I guess. Help session on Thursday at 8:30 p.m. If you want help this afternoon, so I've got today, that's all every Monday and Wednesday, 1 to 5 p.m. for appointments. You can just let me know after class. I do have a couple freshmen coming from 3:30 to 5. I can try to work you in if that's the only time you can make. Otherwise, if you don't want to have me jumping around, earlier is better. Let's see, what else? We got lab when we come back. What is it? It's there might be it's going to be so hard with break. Maybe we won't do a pre-lab again for that. Yeah, we won't do a pre-lab for that one. So in terms of lab reports, someone was asking me if we could not have the lab reports due on Tuesday when we get back, that it would be helpful. I guess there's some early exams. I could do it Wednesday. So shall we do that? Okay, so lab reports due, and I don't have those directions up yet. Lab reports due Wednesday after break at 11:59 p.m. I've gotten way behind on lab reports. I'm going to use break to catch up, so I don't want to get way behind again by pushing these things back too much. I think that's about it. We've got break coming up, so there's not so much stuff to talk or worry about. Did I miss anything? Okay. All right. So we were talking about hemoglobin. Question?
Did you ever find a way to fill lab reports?
Yes, I did. That's a good thing. So, but Lorenzo, I saw an email from you. I wasn't able to read. Did you try to submit it and it didn't work?
No, it wasn't that. It just
But you. Okay, I'll look at your email then for that. So I did figure out. I was taught. Dr. Anderson showed me where the secret button is to press to make that happen. So from here on out, they will all be open so that you can turn them in later. And what I get is I know when they're turned in. So and then I make a decision based on how late it is. Okay, so there is a policy for how late things are, so you should be trying to get things in. This last lab, I said, yeah, turn it in when you want, right? If you don't have it in by now, please get it in before break, because I'm going to get to it then. Okay? Yeah. What was that?
You want us to submit it like today?
We
emailed you.
The one you emailed me, will you please resubmit those to turn it in? If I go through and I rip through them and it didn't work, it didn't work out and I missed it and it wasn't there and I didn't find it in my email, we can fix that later as well. Okay? All right. Sort of clear? All right, so that's when those lab reports are due. The last lab, please get them in by, the Monday of break if you haven't already, okay? And then you'll be able to turn in things late and you won't have to email them to me going forward because I know how to do that. All right, we were talking about hemoglobin then. And we made a big deal about iron, right? Remember we were talking about hemoglobin is really what we care about, what we're going to get to here. We're going to talk about myoglobin first because it's simpler, but very similar. Hemoglobin is an an oxygen transport protein. Okay, and like we said last lecture, transport means you pick stuff up and you drop it off. It has to pick up oxygen in your lungs and drop it off in your tissues. All right, myoglobin is an oxygen storage protein. All right, and so myoglobin is in your muscles. It's in deep sea diving. Mammals have even more of it. So they'll store oxygen. It picks up oxygen and holds it really tight. Now it has to release it at some point or else it never gets used, right? But it holds it much tighter than hemoglobin does. So that's the difference between those two. If you had myoglobin in your blood, it would pick up oxygen in your lungs and it would not let go. It would just wave as it went past your tissues and your muscles, and would just keep the oxygen from there on out. So I've got a picture of red blood cells down here in case you didn't know. You got your red blood cells, right? They transport things around in your blood, but they are this color because of hemoglobin. Okay, it's all hemoglobin that does that. So if we look at the two structures here of myoglobin and hemoglobin, so this is what myoglobin looks like. It's a single subunit protein. This is what one of the 4 subunits of hemoglobin looks like. There are 2 alpha and 2 beta subunits, and I don't care whether you know that. I care that you know there are 4 subunits, right? And the difference between hemoglobin transporting versus storing is that we'll find out the quaternary structure is what's really important for that. The 4 subunits of hemoglobin essentially talk to each other and cause each other to change shape. And so hemoglobin will have a high affinity for oxygen in your lungs, and will have a low affinity for oxygen in your tissues, and that's why it drops it off, because it changes shape. And the 4 subunits talk to each other and cause each other to change shape, and we will talk about how they talk to each other on Friday. But what do you think's involved?
Charges.
Charges. I love it. All right, so let's talk about one of these subunits then. So there are 3 major parts of one of these subunits I want to talk about, and all of the the goals of all these subunits are to reversibly bind oxygen. Yes.
You said there's 4 subunits?
There are 4 subunits. There are 3 parts. Did I say subunit?
No,
There are
no,
3
I was-
parts. Okay.
yeah, you did.
3 parts to a subunit. And you could mention other parts, but these are the parts I want you to focus on. So one of those is an iron in the +2 oxidation state. Okay. The next part is a porphyrin ring. Okay. And the final part is the actual protein itself. So if we think about this, our iron is this red ball. The porphyrin ring is the structure you see around in red around the ball, and then we have our alpha helices here in ribbon form. That's our protein. And I might refer to it as a peptide because it's an individual chain. All right, I want to talk about each of these and how they're important to the function of hemoglobin and myoglobin. So let's start out with the iron. The iron +2, or in the +2 state, can bind reversibly, or can bind oxygen reversibly. Okay, iron in the +3 state does not bind oxygen. And by the way, I'm writing oxygen here. When I say oxygen, I mean O2. Okay, so let me draw that real quick. So for all of our discussions of oxygen here, I mean diatomic oxygen from the air. So the problem here is that free iron 2 will spontaneously oxidize to iron 3 in the blood. So free iron 2, I'm doing 2 here, it's iron Fe +2. Free iron 2 will spontaneously oxidize to iron 3. All right, so this is why we need these other 2 parts, because if you didn't, if iron 2 just reversibly bound oxygen, that'd be enough. You could just have iron floating around in your blood. okay? Which you do, but you've got a lot of other things around it to keep it in its iron plus 2 state. So the problem, one thing I didn't talk about, I thought about and then I didn't talk about it, is oxygen is not very soluble in, I guess I'll write it here. Oxygen is not very soluble in blood, any kind of aqueous solution. Anybody know why that is?
The equal sharing of electrons between the two molecules makes it like non-polar and
Perfect. Perfect. It's nonpolar, and it's nonpolar because, you know, if we want to decide whether it's polar or not, what's more electronegative, oxygen or oxygen? They're the same, so they're going to equally share electrons. We don't have a dipole here. This, nitrogen, hydrogen, helium, none of these things are very soluble in liquids, right? And so the meaningful distance that oxygen can dissolve in your body or in aqueous solution is about that much, okay? And there are lots of parts of you that are farther than that much from the surface, right? This is why you need lungs and a bloodstream and hemoglobin. All right, so what do we need to do? We need to keep that iron in the +2 state, and that's where our porphyrin gets involved. So what I'm showing you here is an iron bound by a porphyrin ring, okay? The whole thing is called the heme. So the iron plus the porphyrin is called the heme, but we're gonna talk about the porphyrin here. So the porphyrin bonds to the iron and stabilizes the +2 state. Okay, it does this through coordinate covalent bonds. Can anybody tell me what a coordinate covalent bond is? It's when one atom donates both electrons. Okay, so what's going on is the nitrogens are donating the electrons here to the iron. So you could imagine iron could be +2 or +3. If you start pushing electrons at it, it's going to like rather stay in +2 than go to the +3 state. Okay, so we now have another molecule or another structure that's stabilizing the iron in the +2 state so it can reversibly bind to oxygen. All right, and if this was good enough, then your body wouldn't have to make a big old hemoglobin protein. All it would do is it would make a porphyrin and you'd have porphyrins floating around your blood, right? But is that what happens? No. Okay, so this is still not enough. What can happen is you can have an oxygen bind to this side of the iron and an oxygen bind from the other side of the iron, and that'll oxidize it to iron +3. So we need the protein. So this is a we don't have much of the protein here, but this shows kind of what's going on. So the protein helps to reversibly bind oxygen in 2 ways. All right, the first way is it binds to the backside of the porphyrin ring. I'll just call this the backside, right? You could call either the backside. This, but it binds the backside iron on the from the backside of the porphyrin ring, and it prevents oxygen from binding on that side. Okay, and as I just said, if we had oxygen bind from both sides of the ring at the same time, we would oxidize the iron to +3. Okay, questions on that? So now we prevented that extra oxygen from binding. And then there's another thing that's important for reversibly binding oxygen, but it's actually not directly related to the oxygen. So, let's see. You ever start your car in the garage before opening the garage door and have your dad freak out? Why is that?
Carbon monoxide.
Carbon monoxide, right? Your car makes small amounts of carbon monoxide, more than, I mean, we have carbon dioxide around us right now in very small amounts. Your car makes more amounts than that, and keeping the door closed would mean you have so much that it would actually kill you if you did it for very long. Okay. So you could also have problems with water heaters or things if they're not burning. If they burn poorly and don't get enough oxygen to them, they make more carbon monoxide than carbon dioxide because you can't fully oxidize the fuel. So carbon monoxide binds to the iron very tightly. Okay, and in fact, it binds. Now I need my notes to make sure. I think it's 20,000, but it might be 200,000. 20. Okay, 20,000 times as tightly as oxygen does. And this is why it's so dangerous. It can bind to the iron where the oxygen's supposed to bind and just stay there and stop your hemoglobin from actually being able to pick up oxygen. So what the protein does is the protein encourages the oxygen binding. Okay, I'll show you in a minute how that happens. And it discourages the carbon monoxide from binding, such that carbon monoxide only binds 200 times as tightly as oxygen. And that's why we're not all dead right now, okay? Because there is some carbon monoxide in there. So let's say not it, the protein. Such that CO, so it encourages the binding of oxygen and discourages the binding of carbon monoxide such that CO only binds 200 times more tightly than oxygen. Okay, we're going to talk about how it does that. So let's first talk about how the protein encourages the binding of oxygen. All right, so the protein encourages the binding of oxygen by making a hydrogen bond with the oxygen from a histidine above the ring. Okay, and that's shown in this picture right here. So we have our histidine below the ring that's preventing anything from binding. And when we have an oxygen bind there, it's canted off at an angle, and then we can get a nice hydrogen bond there. Why is the oxygen canted off at an angle like that? Draw Lewis dot structure for oxygen.
Where the lone pair is.
That's where the lone pairs are, right? So if we draw our Lewis dot structures don't show us shape, but you know, we often, as we get to be more experienced as chemists, we often draw them in the shape anyway. Right, and so what I've got is essentially this is, I mean, what's the hybridization here? sp2, right? Got sp2 here, I've got a double bond. All right, and then these two are going to stick out at angles. This is like trigonal planar, yeah? Okay, so, but this is at an angle and this is at an angle. So do you see if I take this, actually I should have drawn it more canted. Let me do that. But do you see if I draw it like this? We're set to have the His up here and the iron down here, like that. Okay, so we have a hydrogen bond here and the iron bonding there, and we've got the angle, and it's really nice and it fits just great. Does that make sense? Yes.
This might be dumb, but why is that trigonal planar instead of like just like a linear?
Well, the molecule is linear because there are two atoms,
Yeah.
right? But if we think about I'm teaching Gen Chem right now. We think about the electronic geometry. The electronic geometry includes the lone pairs. So when I did that, that's
Okay.
thank you for asking, because that's a good clarification. The electronic geometry includes the lone pairs, and that's trigonal planar.
Okay.
Other questions? All right, so we've encouraged oxygen from binding. How do we discourage CO2 from binding? Well, I didn't have a good picture of this, so I need to find my white pen and white this out. Don't even remember where's white.
It's right there above.
There, thank you. Okay, so now we can white out our oxygen, right? Okay, so this is what it looks like. What does our Lewis dot structure for carbon monoxide look like? Go ahead and draw that real quick. You see, Lewis dot structures are useful. Lewis dot structures are so amazing because they don't at all reflect really what the world's like. But it's a simple model that tells us so much or predicts so much. Yes.
It has to be history as the one above. Sorry, I meant to ask that. And I
Yeah.
forgot. Yeah.
It is history.
It's always history.
It's always history. Does it have to be? Could you substitute another amino acid in there in the lab and maybe make it work? Probably not, or it could maybe work and maybe work okay. I don't know. I mean, you need a hydrogen bond donor. Histidine's really special. It's got that nice pKa of 6, at least before it gets in other things around it. So what did you come up with? An oxygen bound to a carbon. Okay, great. Like that. Okay? So do you see, I turned it the right direction to talk about it here. Do you see where those lone pairs are? So here we have our linear. Actually, if we think about our electronic geometry, we have linear here. And so the carbon monoxide is going to bind like this. Okay? And so it can't make a nice hydrogen bond here because its lone pairs are here and they're sticking up. And even worse than that, because it sticks up straight instead of going up at an angle, it bumps into here. You have a steric clash. All right. I'm doing the best I can with my artistic skills here. But there's going to be a steric clash here. Okay. And we had no hybridization or no hydrogen bond stabilization. All right, so it helps oxygen to bind tighter, and it prevents CO from binding with the steric clash. Daniel,
How does it still bind 200 times better if
it's just a much better kind of bond. Dr. Hughes might be able to answer that better. What was that?
between the iron and the carbon?
Between the iron and the carbon, yeah, it's a much more favorable bond. I don't know the answer. I should. I should have thought of it before. I'll ask Dr. Hughes because this is one of those, you know, if you've had, I don't know if you, how many of you have had inorganic. Okay, so did you cover it? Do you remember why CO the carbon double? I mean, it wouldn't be for this particular, but why is this bind much more tightly?
I don't remember.
Yeah. So Dr. Hughes will know. I'll try to remember to ask him. But this is a much tighter binding ligand to an iron than oxygen is. Other questions? Yes.
So, you know how, like, we get a lot of information when we have a cut or something that has to do, does that have to do with the histamine that's attached to the hemoglobin?
Do you know how that we get a lot of, what was it when you get a cut?
Inflammation.
Oh, inflammation.
Yeah.
I don't think that it's related to CO in terms of that. I mean, it's recruiting your immune system. I read this book, Immune, a year or more ago. I should bring it in if anybody wants to borrow it. It's done by, you guys see the website? It's Kavertz. I can never say it. It's German. Kavertz, whatever. They do things cartoons. They like ducks. Can you say it? Can you say it correctly? Okay, but yeah, the guy there did a book on the whole immune system and how it works, and it's a really great book. Nice short chapters, but that the inflammation is about recruiting the immune system to take care of bacterial invaders and things like that. That's what the inflammation is really about. And I don't think it's CO mediated. If that's what was that your question, or was that not?
Just related to the histamine on the hemoglobin.
Yeah, I don't think it is. So, are you thinking about histamine?
Maybe.
Okay. Yes, Chloe.
So would then carbon monoxide here be like linear?
Yes.
That's
The electronic geometry is linear. It is standing straight up, and so it bumps into, even though it's just 2 atoms long, right? It stands straight up. It bumps into this histidine, which makes it harder for it to fit in.
Okay, whereas O2 kind of
O2 is at an angle when it comes in.
Okay. Wait, I'm sorry, this molecule is. Sorry.
Carbon monoxide.
I mean the big thing, it's just W.
I can't hear the question.
Like what's the gray and the red?
The gray and the red is parts of the protein.
Okay.
Okay, great question.
Sorry.
No, thank you for asking that. So this is our porphyrin ring. This is our iron. And then all the gray is protein. They're side chains off of the protein around it.
Okay.
Okay? Maybe that helps with what you were asking as well. Okay? All right. Well, I'm going to save this until next time. What I want to do now then is I want to change gears, okay? And what we're going to talk about now is we're going to talk about how you can predict how tightly something will bind to a protein. So we have hemoglobin, which we haven't talked about how it has these complicated things where it changes affinity based on shape. But myoglobin doesn't do that. So it's a simple protein system, and we can model that, and we can predict how tightly it binds. And this is something that gets done in terms of drug design all the time. People care about this. So what we've got is we've got a single sub, and this works for, you want to have this work for a single subunit protein, or if you had more than one subunit that they don't really talk to each other. Okay, they don't cause each other to change. All right, so we're working on protein ligand binding math. All right, so let's think about let's have a very simple system. We have a protein plus a ligand, and that can come together to make a protein bound to a ligand. All right, so we can model that. We can do that with we can have an association constant for that. So Ka is those two associating with each other, and that is the protein, and so that would be products over reactants. Okay, concentrations of products over reactants. Now, when you do these sorts of measurements, generally when you purify something and you're trying to measure it, you don't have a lot of the protein. It's hard to make a lot of a protein. And so the way your math is, we want something where that has no protein in it. In terms of, we don't want to have to measure the protein ligand concentration because that's hard. We don't want to even have to measure our protein concentration if we can help it. What we'd like is to have something where all we care about is how much ligand we have, and that we can figure out what our binding constant is based on that. To do that, we're going to need to come up with another equation. So what your book uses is y for this, and what y is y is the fraction of protein sites bound by ligand. All right, now that's a fancy, more general way of saying, in this case, we could talk about how many oxygens are bound, right? What percentage of our hemes are bound by oxygen? Okay, does that make sense? All right, so, and what that's going to be is that's going to be how many of our protein sites are bound, right? Divided by, so it's a fraction, it's like a percentage, but divided by 100, over how many of our protein sites are free plus how many of our protein sites are bound. Does that make sense? What this is? Okay, so we just made that equation up. It, of course, is going to be true because it has to be. Okay, right? Looking at it. So now what I want to do is I want to rearrange my equation on the left so I can substitute into my equation on the right. All right, so I can multiply both sides of the equation by P times L, right? And then we'll get that. You guys follow with that? I multiply this side, this will cancel, multiply this side, comes up here. Okay, so now I can substitute this here and here, right? Because I know what PL is. So if I rewrite it down here, I get fraction of sites bound is equal to concentration of P over L times Ka over concentration of P, I didn't touch that one, plus concentration of P over L times Ka. All right, so I just took this and I put it there, and I put it there, and I got this. Does that make sense? You see something I can cancel? I can cancel what? I can't cancel Ka because I don't have Ka in this piece, right? But I can cancel the P's, right? I can cancel protein out of all of this, which is great because I didn't want to have to measure that. Okay, that's hard to measure that. All right, so if I cancel all those, and I could do that because I have P on the top and I have P in all the terms on the bottom. All right, so still doing blue. So that's going to leave me with the concentration of ligand times Ka over 1, right? I'm canceling, but when I cancel, I divide the top by P and divide the bottom by P, right? So that gives me 1 plus ligand over Ka. That makes sense? What I just did? Okay, great. And so now I can divide both sides by Ka. All right, so let me do this. I'm gonna actually show this. I'm gonna go Ka. I'm gonna divide this by Ka. I'm gonna divide this by Ka. Do you see if I do that, this cancels and this cancels? And I'm going to get my fraction of sites bound is equal to my ligand concentration over 1 over Ka plus ligand concentration. All right, so now I'd like to get rid of that 1 over Ka. And I'm actually going to do this as much to get rid of the 1 over Ka as just by convention people like to talk about dissociation constants. All right, so if you remember, Ka is equal to products over reactants, right? For this reaction, the association reaction is this, okay? The dissociation reaction would be this. And so my dissociation constant is going to be equal to products over reactants like that. And do you see that this is just that divided by 1? So if I take Ka and I divide it by 1, I would just flip this. Yeah? So I get this. So 1 over Ka is Kd. So the dissociation constant. And this is what people that are making drugs and things like that, this is what people love to talk about. You have a Kd, okay? And a good drug will have a Kd that is nanomolar or smaller. I'll do it 1 times 10 to the negative 9th molar or smaller, so nanomolar. Because you want a drug you don't have to give somebody a lot of, right? If you have to give somebody a lot of something, then there's more likelihood that it's going to bind to other things it's not supposed to and give you side effects. All right. Doesn't mean that a really tight binder might not bind a lot of stuff. You need something specific, and there are all sorts of characteristics for a drug. And Dr. Dan, if you haven't had PharmChem yet, I think Dr. Dan will probably teach it next year. I'm not sure. I don't remember, but it's a good class for that sort of stuff. Okay, questions? All right, this is a really cool equation because we can tell stuff from it. It's also going to be sort of related to our next equation. There are some things we'll do in kinetics as well. So what does this equation tell us? We've got this thing Kd, right? If I think about a drug binding to a protein, let's say, now I got all onto drugs, right? We were talking about hemoglobin. This could be oxygen binding to myoglobin, right? But whatever our ligand is down here, okay, we've got our ligand concentration down there, and we have Y over here. Remember, Y is your fraction of protein sites bound. And you'll get the equation says you'll get a curve like that. Okay, we'll talk through why you will by just looking at the equation. But look at this. So what if I had half my protein sites bound? So what if half my protein sites are bound? Okay, so what's the value of Y when half my protein sites are bound? Let's keep our equation on there. Not a trick question. 0.5, right. Okay, so it's 0.5 is equal to the concentration of ligand over Kd plus ligand. Let's go ahead and do some algebra because we love algebra. I do at least. Okay, so you saw what I did there, right? I multiplied the bottom times both sides. Okay, Guys with me? I'm going to subtract 0.5 ligand from both sides. Right? You guys okay with that? All right. And then I'm going to just cancel these. So in the special case, remember what do we start with? We took our equation, we put in half our sites are bound. In the special case where half our sites are bound, what happens? The KD is our concentration of ligand. So when half our sites are bound, let's say that this bound like up to 100%, we had data for that. I'm not going to go 100%, but we'll do, it's fraction of sites bound, right? So 1, right? 0 to 1. Well, if this binds wherever, if I know where 1 is, I can follow it half on up, and I can follow it down, and this is going to be equal to KD. Isn't that cool? So I can, if I have this graph, I can determine KD from it. I can also mathematically, put numbers in and stuff. Okay, so all I need is I need to know how much ligand I'm dumping into solution, right? The assumption here is I have very small amounts of protein, right? So I dump ligand in, and the amount of ligand that binds doesn't change in terms of its concentration, right? Because, so I've got lots more ligand than protein. If all of it binds, my ligand concentration is effectively what I started with. And I dump that ligand in, and if I have some way of measuring what fraction of sites are bound, I could then do this plot to get the information out. I don't need to know that it's bound or anything. I just have some measure of it. So for hemoglobin, this might be it changes color, right? And you guys may have experienced this when they put those little oxygenator meters on your fingers. That's doing spectroscopy on your finger. It's looking for the difference in color between hemoglobin that has oxygen bound and hemoglobin that doesn't have oxygen bound. Okay? So they're not measuring a concentration, they're just measuring the color. And then you can back the concentrations out of that. Does that make sense? Okay. So that's where this stuff is useful. I showed you the derivation there, and there's a 45-minute derivation we'll see in the future. So this wasn't as bad as it gets. Okay, you don't need to know this derivation. Okay, but I'm mostly showing it to you to hopefully get across that all these equations we have in chemistry, they just come from making some simple assumptions, right? If we believe that this is true, and that this is true, right? Well, this we made up, it has to be true, right? The sites bound has to be how much is bound over how much there is, right? In terms of protein sites. Then we just did the basic algebra to the rest of it, and out we popped this really useful equation. And lots and lots and lots, unless you're going to do quantum mechanics, lots and lots and lots of stuff in chemistry, or most of chemistry is going to be this sort of stuff. Questions? All right, well, let's use the equation to solve a problem then. Let's say we're talking about antibodies. Good antibodies bind things really tightly. So an antibody binds its antigen. Oh, let's make it more specific. Binds the spike protein of SARS-CoV. Okay, COVID-19. Where do I put the 19 in that? Maybe I don't. Oh, is it 2? Okay, yeah, that's what it is. All right. So an antibody binds the spike protein of SARS-CoV-2 with an affinity of, let's say, 1. Well, let's make it 0.15 nanomolar. If the concentration of spike protein is, well, let's say 5 nanomolar, Nah, that's too high. Let's make it 0.3 nanomolar. What percentage of the antibody is bound? Okay, let's take a look at this. So our equation is this, right? Notice it's a capital K, not a little k. So you have the pieces of this equation. Let's talk about something else first, though. So we have our antibody concentration is in nanomolar, right? Our affinity is in nanomolar. Our antibody concentration is in nanomolar. Do we need to change those to molar? Why not? Because they're a ratio of the two, right? So you don't, these have to match, right? If I'd given you these in different units, you'd have to make them match, but these are, you're dividing these, right? We don't have, so, and we're adding these together. We're not multiplying our units. So we're gonna have nanomolar, nanomolar, that's gonna be nanomolar. And so the answer out here is actually gonna not have units because it's a fraction. Okay, so you're gonna do that. And then I did something a little tricky. I asked for the percentage. So you want to get your fraction out and then make it into a percentage. Why don't you go ahead and try that? Okay, that's not how you're supposed to do it. I figured I'd just do some stupid graph stuff and see how close I got. But so what you should be doing here, right? You've got your concentration of spike protein is 0.3 nanomolar. So that I'm going to get that there and there in my equation. Plus my KD here is going to be, what was it? Was 0.13? 1.5, sorry, thank you. Nanomolar. And that's equal to this. If we go ahead and put these together, I'm going to get 0.3 nanomolar over 0.45 nanomolar, which this is going to end up being 2/3, yeah? This is going to end up being, so 0.66 or 67, and then 66%. So I didn't do very well there, did I, with my stupid graph stuff? But yeah, I would have hoped I would have done better than that. Anyway, you see how to solve that? Okay. Let's talk really quickly in terms of just equation understanding. Yeah.
Affinity is synonymous with KD.
Yes.
Okay.
But so something that's fine, but let's talk about that. KD, right? We're using a dissociation constant. So something that binds tighter, does it have a higher number? Does it have a higher KD? Or is it a larger number? Or does it have a smaller number? Smaller. Right. Okay, so that's a little counterintuitive. The smaller the better. And you know, like I said, people are making drugs. They want those things as small as possible. Okay, let's talk about the equation and this graph though here. All right, so why does this graph look like this? And I want you to kind of get some graph sense or equation sense where you can think about what's going to happen with this. So when I have a low concentration of my enzyme, or not my enzyme, of my ligand, right? If I have a low concentration of my ligand relative to KD, what happens? Let's pretend KD is 1,000,000. Well, let's make it, what's that, 100,000. It's 100,000, okay? And then my ligand concentration is 1. All right. If I then change my ligand, so if I do that, I'm going to get what? I'm going to get 1 over 100,001, right? That's going to be what y is equal to. Now let's say I double at that very low concentration, I double my ligand concentration. Now it's going to be that, right? So what happened to my fraction of sites bound between when I doubled my concentration effectively? Not nothing. It doubled, right? My numerator doubled and my denominator stayed the same, right? So at low concentrations, we expect this graph to go double, 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 okay? We're expecting it to double every time you double your concentration. We expect it to be linear with ligand concentration down here. Okay, you see how it's kind of a straight line the way I drew it? This isn't real data, it's me drawing. Okay, but it's going to be linear there. What happens when the reverse is true though? Let's go draw it down here again. So remember our equation is this. Okay, what happens when we have this? So let's say I have really big numbers and I'm way over KD. So let's say KD is now 1. Or we can keep KD the same, right? It's 10,000. But now my ligand concentration here is like 100 million. Okay, 100 million, right? And I've got 100 million up here. 3 million's a big, 100 million's a big number. Okay, so what this would be at that case, we'd have y is equal to 100 million, 1, 2, 3. This is why we use scientific notation. Okay, 100 million over 100 million. I think I need another 0 there, and then 3 zeros in. This becomes a 1, right? Okay, do you see that if I double at this concentration, now my ligand concentration is way higher than KD. Now if I double it and I make this 200 million, and I take the bottom and I make it 200 million instead, has it changed much as I doubled it? Right, so when I get way over KD, when I was way below KD, when I add ligand, I got a linear response, and when I'm way above KD, nothing changes as I add more ligand. Does that make sense? And in between, you transition between the two. I'm partially doing this because these are the exact same plots we'll see when we do kinetics. And this is important, but if anybody ever asks you one question from this class on a test, or wants you to know something, if there's only one thing they want, it's going to be kinetics. Okay? So this is similar, we're sort of prepping for that as well. All right, it pains me to do so, but I think I'll let you guys go early.